Maybe we can start and people will join us. I just start with a short introduction. So thank you everyone for joining on time. We will probably have more people. We have more registered people, but now we have several participants from all over the world. So let's see to who I should say good morning now. Raise your hand. And good afternoon to who? Hi. And good evening, right, Rachendra? I think it's for you.
Yeah.
Yeah. Okay, so great. I just want to give you a short background of how everything started and led us to this point. So 2 years ago, Nicole and I organized a virtual symposium on mechanistic reasoning, and some of you also participated in this symposium. We talked about mechanistic reasoning in science education, and a short period after this symposium, since we saw that so many people are interested in mechanistic reasoning from different fields in science education, we decided to edit a book on mechanistic reasoning. So, and we invited also Rachendra, who's also here today, to participate and edit the book with us. And I'm glad to say that in about a month, it's going to come out. It's already in a Springer website, and there are several very interesting chapters in this book exploring mechanistic reasoning. And then during the process of creating this book, the AI revolution started and started to affect us all. And then we thought that it's a good idea to think about mechanistic reasoning in times of AI. It can affect us in many different ways. And today you're going to hear about how we can use AI to support mechanistic reasoning, or how AI challenges mechanistic reasoning, and also how we can use it in research. So we are going to have 5 different presentations. After each presentation, we will have time for questions. And at the end, we are going to have a general discussion, a group discussion. We are not such a large group, so we expect all of you to participate in this discussion and think with us about this idea of mechanistic reasoning in the age of AI. And I also invite you, when you hear the talks, if you have a concrete questions, it's okay. We can ask it in the times for question for each individual talk. But if you have more general questions or idea, even philosophical ideas, you can write it down in the chat or in private to me or to Nicole. And at the end, in the group discussion, we can use these questions to anchor our discussion. So without further ado, I'm going to present our first speaker. We will start this session with Rachendra Bertier, who will present his work about the use of AI to support the research on mechanistic reasoning. So Rachendra, the floor is yours. You can share your screen.
Yep. I hope you can see my screen now. Yeah, thank you. Okay. Good morning, good afternoon, or good evening, everyone. First of all, I would like to say thank you so much, Michal and Nicole, to make this event happening today, and also thank you for all joining our interested events. I'm going to talk about my research experience on mechanistic reasonings and how I use some kind of AI to support my research on mechanistic reasoning, especially for AI. This is my personal experience, and maybe because I don't have a lot of knowledge about AI, but very few knowledge, I'm trying to use that knowledge to research on mechanistic reasoning, and I'm going to share about my personal experience. before that, a little bit about my research projects. This is about still mechanistic reasoning and also still stop motion animations. But there is kind of modeling based in quiet learning that I involve in stop motion animations, and how modeling based learning and using stop motion animation in this kind of sequence of learning to support mechanistic reasoning. And this is my ongoing project. And the general research question that we would like to address is, to what extent does constructing stop motion animation in the context of mobile modeling based learning promote mechanistic reasoning? This is my overview of research. And just to let you know that what is stop motion animation, this is kind of one of the stop motion animation created by my students or research participants. This is about mechanical energy. Um, um, I think all of you are understanding about what is mechanistic reasoning. Just give you an overview. What is mechanistic reasoning in my research project is about energy transformations. My research is in this energy is about free fall motions. And what is mechanistic reasoning in terms of free fall motions? I'm gonna let you know this is one of an example of students, what student mentioned about um, free fall motion, how potential energy transform to kinetic energy, and what is mechanistic reasoning is in this context. And of course, we use 7 element of mechanistic reasoning by Russ, and also I published mechanistic reasoning literature review on mechanistic reasoning. I see there are 2 basic elements of mechanistic reasoning should be happening when students want to say in mechanistic way. The first one is the first basic element is entities, and you can see these basic entities in potential energy and kinetic energy. And also the second basic element of mechanistic reasoning is what entities do, or activities of entities. And in this case, these students say because potential energy changes to kinetic energy. So we can say this is mechanistic reasoning, how mechanistic reasoning appearing in these students' mentions. And then I would like to understand whether creating stop motion animation and involve these animation activities into modeling based learning can support this kind of element of mechanistic reasoning. And then this is I'm combine SMA construction, or stop motion animation construction, and modeling based in quiet learning. And I'm gonna give you kind of overview what is stop motion animation is. Stop motion animation is just very simple. If we want to create stop motion animation, we just need to use, of course, we need to use specific software or stop motion animation software, and then we use that software to capture an image we would look like to do. For example, picture 1, picture 2, and picture n. And then it's gonna be stop motion animation. It's very simple. In our research also, we say that to construct stop motion animation, we need to do two activities. We can say chunking and sequencing. The first one, chunk, means we can say the first picture. The second picture is chunk 2. And when we order this all picture, it means we sequence all the picture. And we are trying to involve the animation construction in modeling based in quiet learning. This is kind of how modeling based learning looks like, the step by step an instructional sequence. This is like a student need to create a model in terms of stop motion animation. in the beginning, the model we can say is like an office model, and then step by step, this model grow gradually and becoming into expert-like model. This is like something like that. I'm not going to make a detail what is modeling based inquiry learning, just give you an overview. And then, as I said before, and then I try to do data collection and pre-intervention, and this with task-based interview, and then with 15 secondary science students in terms of mechanical energy. And we use pre-intervention. We collect data in terms of pre-conceptual understanding, and then we apply intervention, modeling based inquiry learning, and stop motion animation about free-fall motion. And then after that, we took the data in terms of post-conceptual understanding. And as I said before, general research question we address is to what extent does constructing stop motion animation can promote mechanistic reasoning. And uh, and then, as I said before, when I use AI in terms of my research, as I said before in previous, this is my research, and when I use AI. I use AI in terms of two activities. The first one, when I took data, I use kind of AI for auto transcription and also data analysis. I use two different type of AI. For the first one is, I think we are so familiar with our Microsoft Word, MS Word. There is kind of AI embedded in our Microsoft Word, automatic transcription, and all of data analysis. I use a very popular AI we call ChatGPT in that case. I'm going to show you how I navigate this AI. For using auto transcription during interview, I use Microsoft Word because my data collection, when I took the data, I apply interview. So I use Microsoft Word. When I'm interviewing students, it automatically transcription. I just give you an example how I use this one. This is just an example how to use auto transcript in Word. As you can see in the screen, when I say something, it's automatically transcribed in the Microsoft Word. So it's really helped me. I don't have to play again in one day. Just an example of how to use auto transcript for the right picture. This is the example of how auto transcription happening in Microsoft Word. And what is opportunities and challenges I face when I use this one? The benefit I got is, of course, keep the time consuming transcription. It's very hard for me if I have to play back what I was interviewing and trying to make it translate into text. Is very time consuming, of course. So when I use that one, that AI is very helpful for me. But the challenge is the accuracy of language detection. It's very hard. I need to make sure there are no any typo or something. For example, in the blue one, it should be in this is not really good in Bahasa Indonesia, of course. So I need to check first. And sometimes I don't know, I don't really understand what this text is about. So I have to recheck it in the audio recording. And also we need to reorganize the transcripts. As you see, I don't know where is a researcher and where is a student. saying. So I need to make sure. This is the challenges I found when I'm using auto transcription using Word, Microsoft Word, I mean. And the second one is for data analysis. This is not, I'm using ChatGPT as co-researcher or assistant researcher. I try to compare between ChatGPT and what I do in data analysis using NVivo. And of course, when we use ChatGPT, we need to make sure the ChatGPT understand what is mechanistic reasoning. I need to teach the ChatGPT the 7 elements of mechanistic reasoning, and then I apply what ChatGPT know about mechanistic 7 elements of mechanistic into my data. And what I found is the opportunities again is, of course, there is kind of a new insight that I found when using ChatGPT. Sometimes this is good, and I need to think about what ChatGPT say, what ChatGPT code in terms of mechanistic reasoning, and of course reduce human error sometimes, because sometimes when I code using NVivo, there is something error that I found. It should be entities, for example, but I code it as a property of entities. But the challenges that I found is we need to use appropriate prompt. So this is the big challenge I found, because as I said, I'm not really an expert in ChatGPT or AI, so I need to make sure I use appropriate prompt in order to make sure that ChatGPT can work well. And then I need to do verifications. As you see in the table, I try to compare ChatGPT and human. For me, for the first excerpt, I try to translate into English. This is the first one in Bahasa Indonesia, and in English one, the English version. For the first transcript is okay because we have the same ideas about the coding, entities, EN is entities, ACN activities of entities. But for the second and the third one, there is kind of a big difference. So ChatGPT said this code refers to activities of entities, and for me, this refers to entities and properties. I need to check verification, and verification is needed in this one. So for me, AI is very helpful, but sometimes we need to make sure that for data analysis, especially, we need to make sure our prompt is appropriate, and also verification is needed. But on top of that, I'm going to show you the preliminary results that I found, how mechanistic reasoning happening in the step-by-step of modeling-based inquiry learning. As you see in the phase 1, in the first step, not much mechanistic element appearing, but after that, mechanistic element gradually happening in this one. I think that's all for me, Michal. Thank you so much. I'm gonna really look forward to having discussion with you all. Thank you, Michal.
Thank
You
you,
are seeing.
Mahendra. Okay, so we have time for questions. You can just unmute yourself, I think, if you have a question. I'm not sure I can see everyone. Yes, Paul.
Yeah, thank you very much for your talk. I have a question regarding your characterization of the elements of mechanistic reasoning in students' responses. On one slide, you said that you characterized kinetic and potential energy as the entities. And as I understood it correctly, on another slide, you said that it's rather a property of an entity. And I would go with your second notion, because I would say the ball is also here, the entity, and potential and kinetic energy are kind of the properties of this specific entity that can be transferred into one another. Can you comment on that? Your underlying thoughts?
Thank you, Paul, for your very interesting question. This is kind of a big discussion among our team of research. What is entities, especially in this case, the ball or potential energy? Is very interesting topic when I did data analysis, and we decide that potential energy is entities, and the ball is like the ball itself is not entities, because in this case, when the ball goes down, it says the level 1 of mechanistic reasoning in the RAS. Because why we decide that, I use my framework in the second article I published it. We use and then of course in the quiz as well, we decide entities as something that is abstract. So for this case, potential energy and kinetic energy refers to entities, not the ball. Paul, is it answer your questions?
So you say that entities always have to be on a scalar level that is not directly observable to
Yes,
us.
exactly.
Okay. Thank you for this clarification.
Yeah, thank you, Rahendra. I mean, you raised in your talk an interesting point that all qualitative researching persons are likely to using ChatGPT for coding, and
Yeah.
because I mean that is would be cool to use that. Maybe you can comment on how you are configuring your chatbot. Because I just recently, last week, we just had a talk with Paul Gisgala from the University in Kiel, and he's looking at, on the one hand, linguistic biases that you can see in ChatGPT, and also on the other hand, like time-related differences depending on, if you're using it where like everyone is using ChatGPT, so the performance decreases a little bit. So how did you manage all the difficulties in the reliability of coding with such a chatbot?
Yeah, the reliability is very tough for our research team when we took data analysis, Nicole. Regarding navigating ChatGPT, because our team is not very, as I said, we are not an expert in ChatGPT or AI in general. We make sure that ChatGPT understand what mechanistic reasoning is, especially the framework from RAS. So if I'm not sure whether you can see the screenshot of my first this one. Sorry, this one. This is how we manage, how we make sure that ChatGPT understand of mechanistic reasoning. We start that ChatGPT has certain role, and then we uploaded the text of the article from RAS, and then we make sure whether ChatGPT understand of seven element of mechanistic reasoning or not. So they kind of summarize 7 element of mechanistic reasoning, and we try to make a clarification whether the summary of 7 element of mechanistic reasoning is really correct or not. And then after we see that it's okay, your your understanding on mechanistic reasoning is okay, and then we kind of uploaded the example of the correct answer of students mentions about mechanical energy, and let's see whether the ChatGPT can code this kind of correct answer or not. And of course, the correct answer can demonstrate seven element of mechanistic reasoning. And then for this one, it's very hard because sometimes ChatGPT code this is property of entities, as Paul said. Energy is property of entities, not and then the ChatGPT say the ball is entity in this case. So that is and then we need to reorder. So as I said, we need to make sure our prompt is appropriate. So that's why we need to reorganize or rewrite the prompt, the correct prompt.
Mm-hmm.
And sometimes it's still hard for me, and how we navigate the ChatGPT can work as we want, Nicole.
Mm-hmm. So you haven't really used or configured your own like chatbot in ChatGPT. You were
Yes.
just in the chat, like uploading the paper, and then have you understood what
Mhm.
mechanistic reasoning is? And so you haven't really trained ChatGPT on your context with that ball falling
Yeah.
down. Okay, yeah. So
Yeah.
yeah. Okay, thank you.
You're welcome.
Other questions? Okay. So thank you, Alejandra.
Thank you so much.
We're going to move to the next
Okay.
lecture. So the next lecture will be presented by myself. I noticed that I didn't say anything about myself. So I'm Michal Eskelitach. I'm from the Weizmann Institute of Science. And today I'm going to present together with Moria Arieli our work. It's a very preliminary work that was initiated by my PhD student, Shani Mishal. Shani, are you here? You raise your hand. Hi. And she is going to continue working on it because she came back from her maternity leave. But today we're going to present the first part of this study. It's very preliminary, but we think it is very interesting. The title of the work is The Search for Explanatory Black Boxes in AI-Generated Content. And you can see that we can see the slides. And I need the mouse. Okay. Okay. So I want to start by refreshing our memory for the definition of mechanistic reasoning. So mechanistic reasoning is an iterative process of unpacking a mechanism by considering lower scala level entities and activities and linking them from cause to effect. Now, it was originally suggested by Russ and Chris that it's not just one process, it's an iterative process in which further refining and unpacking of the mechanism occurs. But if we only have these parts of considering and unpacking entities and activities and then linking them to create the mechanism, then something is missing because something should make us go back. Otherwise, it's not iterative. And what we want to suggest is that what makes it iterative is the recognition of explanatory black boxes and the consideration whether these black boxes require further unpacking. And if so, we can go back and unpack these black boxes. Now, before I dive into this, I want to say a few words about what I mean when I say black boxes. If you're not familiar with this idea, explanatory black boxes was a term I suggested a couple of years ago. And explanatory black boxes are the parts in the mechanism that we do not unpack. For example, I'll give an example from biology, and we will continue with this example later on. I can try and explain the phenomenon of hemophilia, the disease that causes constant bleeding. And I can try and explain it and unpack entities and activities in the way. For example, I can say that it starts with a genetic mutation in the gene coding for a specific factor, factor 8. So factor 8 is not produced or just minimally produced. And then in case of an injury, there's not enough factor 8 that can bind another factor. So this complex between factor 8 and the other factor, VWF, is not produced. And when this factor is not produced, it cannot activate platelets adhesion, which is the part that actually make the clotting and stop the bleeding. So here I explained why from the genetic mutation we get constant bleeding after an injury. But if we take a closer look, we can identify several black boxes in this explanation. For example, wait a minute. Okay, I didn't say anything about how we move from the genetic mutation in the gene coding for the factor to the fact that the factor is not produced. The protein is not produced. Now, if my audience has some level of biological background, maybe I don't have to explain it because they know how genes code for proteins. So it means that when we choose black boxes, one of the things we can think about is our audience. Another thing I didn't explain here is what do I mean by activate? I said that the complex of the two proteins activate platelets adhesion. But what is activation? Didn't explain the activation mechanism. But maybe I don't have to explain it, because if the purpose of my explanation now is just to explain why the gene mutation causes the bleeding not to stop, I only want to mention what is the process that is not happening here, which is platelet activation. And I don't want to explain how it usually happens. So again, another consideration about putting black boxes could be the purpose of our explanation. And another example is that I didn't explain anything about the binding between the two factors. And in biology, we usually don't have to explain mechanisms of binding. It's just a black box. But in the discipline of chemistry, it's a whole mechanism. So again, we can see another a feature of black boxes, and we think about them as something that is related to the discipline. So this is why they are termed explanatory black boxes, because they are part of the explanation and they have an explanatory role. We have considerations when we use these black boxes. So these black boxes will appear in all explanations. And as I said, it will appear also because of our considerations, nature of science communication, and the nature of science, of course, because not everything is known. So again, to our hypothesis that was that explanatory black boxes the recognition of explanatory black boxes can initiate an iterative process of unpacking. And if so, we asked, what are students' strategies for recognizing these black boxes? And do they actually initiate this iterative unpacking? And also, what are students' challenges in recognizing black boxes? And we wanted to do this in the context of AI, not just because this was the only way to get into this symposium, but also because we think that AI is something that students use nowadays. And if we want them to use it as a tool for inquiry, we need to see how we can make it something that they don't just get one answer and give it to their teacher or say, okay, I'm done, but something that they could do iteratively. They can work and ask further questions and learn more about the mechanism. So what we did is that, and again, I remind you that this is a very preliminary study. We're talking about 2 pairs of 10th grade students, one male, one female pair. And we asked them to construct mechanistic explanations to two phenomena. One was a genetic phenomenon that they had to choose between two. And another one was an ecological phenomenon. I don't know if you're familiar with this. It's about the wolves that changed the river. And the genetic phenomenon was about hemophilia A or sickle cell anemia. And we gave them the opportunity to use ChatGPT-5. And we asked them to use it to ask questions and to learn about these, the mechanisms. And I just remind you that since black boxes will appear in all explanations, they will also appear in explanations that ChatGPT-5 will provide. Okay, so our findings. First of all, we found that one of the strategies that students used was testing logical consistency. This was one of the strategies that led to the identification, the recognition of black boxes. For example, one student said it says that one important protein in the clotting chain is damaged, but it's still not clear why its absence causes bleeding not to stop. And then his friend said, right, it says the protein is important, but why its absence completely disrupt clotting? They couldn't figure out how just one protein that is not working or absent can damage the whole system. And this was a logical inconsistency that they identified, and it led them to ask further questions and to initiate a new iteration of inquiry. And they asked the chat this specific question. The second strategy that we found was the re-examination of links. So they created an explanation, they linked the part, and then they started questioning their linking. For example, one student said, it should explain, okay, they talked about the ecological phenomena, about how the wolves changed the rivers. And one of their links was between the wolves and the deers. And then the student said, it should explain how, from the wolves being introduced, the deer population went down. And then her friend said, they probably ate them, but we're just inferring. And then she replied, yeah, I need the chat to write that. So they felt that something is missing. I mean, they had a link. They could figure out what's the link between the two. I mean, they could infer about the mechanism underlying the link, but they felt that they are still uncertain, and they wanted the chat to actually write it down. So again, this recognition of a black box initiated further inquiry, and they asked the chat again. Now let's move to the challenges. First challenge we identified was focusing on jargon. It's not new. Many people noticed that, and we also noticed that in other studies. So they said things like, we don't know what a point mutation is. So they focused on this specific jargon, this terminology, while the problem with this is that it actually distracts them from the mechanism. When they try to understand the mechanism, they don't really want to know what a point mutation is. They want to know how a point mutation is involved in the mechanism. And that's a different question. It's not just what it is. And it's something that other studies characterized and show that it's just distract people from identifying the gaps or the things that they actually don't understand, into just considering that maybe it's just a jargon that they don't understand. And it stopped when they had this challenge, it stopped their inquiry in regard to the mechanism. The second challenge was black box perception disagreement, meaning one of the pairs thought that there is a black box, while the other person thought that there is no black box. For example, H said, how does the fact that the cell gets stuck in the blood vessels cause pain? They talked about sickle cell anemia. So the friend said, because it blocks them, they block the vessels. And then H said, okay. Now, she wasn't completely satisfied from this answer. She still felt that there is a black box here. But eventually, she just went with her friend and said, okay, and they stopped inquiry. She didn't ask a question about this. And the last challenge that we identified was heuristic reasoning. It means that when the students just bridge the gap with a heuristic. For example, Anne said, I don't know how beavers build dams. It's a really big black box. Here we can see again an example of a black box perception disagreement, but it is blocked by the heuristic reasoning. So again, Anne said, I don't know how beavers build dams. That's really a big black box. And his friend is saying, but that's just what they do. So this black box was just masked by the heuristic beavers build dams. And it's not a problem to say that it's a black box that is not supposed to be unpacked. I mean, it's okay to say that it's irrelevant, or that for the purpose of this explanation, they don't have to unpack this black box. But in this case, they just say that, okay, so probably there is no black box. And we think that it's important to recognize that there is a black box, but still we say that we don't have to unpack it. Okay, so from this very preliminary study, we can conclude that, first of all, the recognition of explanatory black boxes seems to initiate iterative unpacking, and when black boxes are not recognized, it stops. And second, we found that students demonstrate intuitive strategies for identifying these black boxes in Gen AI generated content, but still we see that they encounter some difficulties. So we asked whether we can use Gen AI to help them. And now Moria will show what we did about this idea. I think you're muted.
Yes, no.
Okay.
Okay. So we have, we know, but after all what Michal said, that supporting students to reason mechanistically requires helping them to identify gaps, test new ideas, refine their explanations, and it should be based on feedback and reflection. But we have two major barriers that exist. First, most traditional assessments focus on factual recall instead of probing students' causal reasoning, so teachers often don't get insights into students' underlying thinking. Second, giving high-quality formative feedback, the kind that helps students refine their explanations, is extremely time-intensive, and it makes it very difficult to provide consistently, especially in large classes. So AI has the potential to help address both barriers. It can analyze open-ended questions, explanations at scale, and provide immediate tailored feedback that supports the iterative refinement process central to mechanistic reasoning. So here you can see our personalized teaching and learning environment. We used a specific example of chat with AI we can do in this environment, online environment. And I'll show you an example from our mechanistic reasoning trainer. It's very preliminary. And the goal of this activity was to present students with a short, relatable descriptions of real genetic conditions and invite them to reason about what might be going on. And I want you to look at the example and focus on the principle, not on the specific details or exact sentences, because as I said, it's very preliminary. So it's not perfect yet. So we have an activity called Chat with AI in this learning environment, and it looks similar to the agent-style chat interfaces that most of us are familiar with. And behind the scenes, what we did is we provided a long and structured prompt that defines how the AI should interact with the learners. And we embedded many of the components that Michal just talked about, using them as scaffold that guide the dialogue, and in the direction that we believe supports high quality of mechanistic reasoning. And students could choose between several genetics phenomena. And here they chose the hemophilia. And no, it's not going. Okay. And here you can see, for example, how the AI interacts with the students once they selected the specific disease, as I said, hemophilia A. And the AI starts by asking students about their goals for the explanation. This is intentional because we want learners to think about what they want to understand. It's not passive reading facts. Okay, it activates reflection about what is relevant, what is not relevant, and it sets a purpose for the learning process. So you can see that even when the student says, I never heard about it, the AI doesn't jump straight into teaching. Instead, it uses one of the scaffolds that we build, which is prompting the learner to define two goals. And this keeps the student in the role of someone actively constructing the explanation. Okay, here you can see. So this is what happens once the student asks the first content questions, and he asks for the ChatGPT to give him an explanation. And he asks, what is it and how do you get sick? This triggers the AI to provide an initial explanation and ask the students to draw a diagram or scheme for this explanation. So next he can draw such a diagram. This is just an example. And here you can see how we visualize the mechanistic chain the AI encouraged the student to draw. So this is the structure that is at the heart of the mechanistic reasoning, linking the gene to the molecule to the function and then to the symptoms. But note that there are unexplained links or black boxes in this diagram. So up to this point, the student has built an initial diagram, and now the AI moves to the next scaffold, helping the student identify unclear or causal links in their explanation. So earlier in the talk, Michal described the important strategy for supporting students in mechanistic reasoning, which is helping them notice the transitions between stages in the mechanism. So we prompted the AI to use this strategy by telling the students to identify which connection in their diagram feels incomplete. So rather than giving the missing steps right away, it guides them to surface that gap themselves. When the students identifies the place in their diagram where they don't fully understand the transition between the two stages, it doesn't automatically mean we should open it up. So then the AI asks the students to decide whether opening up this unclear part is necessary for achieving their own explanation goals from the start of the activity. So in other words, the AI doesn't just give them the missing information, it's prompting them to evaluate whether this specific causal link matters for the explanation that they want to build. So once they decide this connection matters for their understanding, the AI opens that black box for them and asks the students to update the diagram. So you can see that that is reflected in the diagram below. A new level is added, the molecular process box. So this illustrates a key strategy in our design that students are not just given explanations, they selectively open the parts of the mechanism that matters for the explanations they are trying to build. The AI acts as a partner that reveals complexity exactly where and when the students need it. This iterative process continues, and every time, each hour you see, the students can pause, reflect, and decide whether they need to open the next black box in order to reach their explanation goals. And it will keep supporting them step by step until the students decide they have opened enough of the mechanism, and when they feel they covered the causal links they need, it will naturally stop. So our future directions are to continue learning and characterizing student strategies and challenges in recognizing black boxes, to develop the tutoring system further so we can use our knowledge from the characterization phase, and also to research the system and its effects on students' ability to recognize black boxes and relate to their explanatory goals. Thank you.
Thank you, Moria, and myself. Any questions?
I have a lot of questions, but maybe I'll start with one small one. First of all, I really love the work. You've investigated black boxes for a while, and I was wondering, did the learners raise questions or have ideas about black boxes differently with the AI agent versus in your former studies where there was no AI involved?
Actually, we were not in the implementation part yet, but you mean the part when we experienced it with
the initial
not
study.
with the chat, but with the untrained. Just with the ChatGPT.
Mm-hmm.
Yeah, not the chatbot. Okay.
Yes.
It's a bit different because what we are seeing is the actual process of unpacking, while in other studies like Gore, that he will present later today, the work he did with you, in his studies, we saw the reflection of students about black boxes in their own explanations. Now we see how they treat black boxes, that when they try to identify information that they got from the chat, and we see how they use it to further unpacking. So it is a bit different, but it's related to another study that Shani also conducted with undergrad students, in which we gave them a text from the media and asked them to identify black boxes. But in this case, we pointed them to find the parts that they don't understand, and we asked them about those parts. And in this case, we just asked them to create an explanation. So at the beginning, we asked them to choose a purpose for the explanation. And I think that is something that is very different, because when you have a specific purpose, the considerations of whether unpacking black boxes or not are related to the process. And what Shani is doing is that she's using the idea of SRL, where you set your goals at the beginning, and then after a circle, you try and reflect on the goals. So I think that in this study, we can see how they see the goals, and how by looking at the goals, they can actually decide if they have to unpack these black boxes or not. Okay. Yes, thank you, Iris. Go.
Well, thank you. I was wondering whether the decision to use pairs of students, was it a methodological decision or a pedagogical decision, or maybe both?
Actually, both. We thought that the conversation will be better, and also we thought that eventually when people talk and discuss the idea of explanation, we can see other challenges that we would not identify if it's just one student working on his own. For example, the fact that they do not agree about the black box, whether the black box exists or not. It's something that could only raise for this discussion. So we think that it also enriched the research and the conversations that we can hear from them. Tom?
Yes, thank you, Michal and Moria, for this interesting research and presentation. I have a question about the cognitive or metacognitive level demand in this task, because it seems like you expect the students to have a very high level of knowing what is their goal and understanding what they still want to figure out. So is there something in the design of the chatbot, of the AI, that you place to be able to recognize this or to support students in different levels? Because it seems like a very high level task for the students.
As I said, it's very preliminary. I have to mute. And because it's based on ChatGPT, it's very smart. So sometimes when you just don't give the goal, it will ask you again and again, and maybe give you an example. It will give you some ideas. What does it mean to give a goal? I don't know if it's good or not, and we haven't tested it yet. So probably when we start doing this with the students, we'll start to see all the challenges and things that we have to improve in this chatbot. Until then, I don't know.
Vanessa?
Thank you for your presentation. Regarding this exploratory study with these two groups of two students, what information did you pass to the students regarding the black box? Did they know that they were looking for black box? Did you explain them what is a black box, that they might find black box in the explanation? What you...
Yeah, okay. And we're still, again, it's a preliminary study. We're trying to see how to move it forward. And this is one of the questions we are struggling with, to what extent we should be explicit in the way we show it to them at the beginning. And one of the things that in this study, what we did is we just presented a story that is not about science at all. It's about a person going to school, and then he had a secret, and someone found out about the secret. It's a very short story with different processes. And then we talked, then we said, okay, so, but what are the parts we don't really understand? So we said that he woke up and got to school, but we didn't really explain how. Were he walking to school? Was it just, he took the bus? But maybe it's irrelevant, because maybe for the story, it's not relevant. So we showed them the idea of black boxes in the context of the purpose of the explanation at the beginning. But we're not sure that this is the right thing to do. Now we're trying to see if we can give them an explanation, a scientific explanation, but a very simple one. We're still struggling with this because it makes a difference, but we think that we should be explicit. Otherwise, they won't know what we're talking about when we ask them to find the things that they don't understand. They just interpret it differently. Okay, I think we have time for just one question. Lachendra?
Yeah, thank you, Michal. In your data, you say that AI helps students to identify the missing link between gene level and protein level. I'm wondering, maybe in your another data, do you have any other student that they are not aware of it, and how, if there is, and how ChatGPT or AI helps students to recognize there is something missing happening in the link between these two?
Mm-hmm.
Thank you.
So in this case, you want to answer it, Maria? Okay. No, maybe you can add to what I'm saying, because I just wanted to say that in our case, actually the student didn't know how genes code for protein. And we were, the interviewers, we were the playing the role of what we want eventually the ChatGPT to do. And we asked them, do you know how it codes for protein? They say no. And they also said, we don't care, because the only thing we care about is that we understand that it's a code. If the code is different, then the output is different. We don't care about the mechanism for this purpose of the explanation. But we are trying to make the chat asking those questions. Maya, do you want to add something?
No, I think it gives a free choice to the students. It has pros and cons. Some students will see the missing connection that we would like them to see, others won't. And I think it's a good process to understand what we need to do in order that the chat will be really good in tutoring students and eventually ask the questions that will help them understand the mechanism.
Okay, so now we will move to our third lecture. And our next presenter is Paul Marting. He will present his first exploration as a postdoc under Nicole Zgarlich's supervision, following his PhD in her group. And the title of this presentation is How Can Mechanistic Reasoning Inform Credibility Judgment of Scientific Information in an Age of Misinformation?
Yeah, thank you very much, Michal, for your introduction. And hello and good afternoon or good morning or good evening also from my side. And thank you very much for being part of today's symposium on mechanistic reasoning in times of AI. And in times of AI, generating and sharing misinformation becomes very easy, which makes critical thinking and fact-checking more important than ever. And in today's talk, I'm going to present our evolving research on mechanistic reasoning in an age of misinformation. Particularly, I'm going to present how we could use mechanistic reasoning as a domain general scaffold to broad phenomena, which may ultimately help students advance their reasoning about the credibility of mediated scientific information. And as Michal already mentioned, I'm Paul. I'm working as a postdoc at the Institute of Chemistry Education at Justus Liebig University, Gießen, in Nicole Kraulich's research group. And today I'm going to share how we could leverage mechanistic reasoning as a lens for approaching phenomena, and maybe also to deal with the credibility of mediated scientific information. But first of all, I would like to start with a general goal of science education. According to the PISA Science Education Framework, a major goal of science education is to equip students with the competence to provide explanatory accounts of natural phenomena by asking 3 questions. What exists? Why does any given phenomenon happen? And finally, how do we know? And these 3 questions correspond to the ontic, causal, and the epistemic question of scientific inquiry. And mechanistic reasoning can help students approach these 3 questions of scientific inquiry. Generally, domain-specific target phenomena can be seen as a starting point for students' mechanistic reasoning. For example, we can observe that the exposed surface of an apple turns brown after a few minutes. And this observation already addresses the ontic question of scientific inquiry concerned with what exists. We can also provide a basic causal explanation for this phenomenon. When we cut an apple, the cells and especially the vacuoles are damaged. Some natural compounds, so-called polyphenols, come into contact with the oxygen in the air. Due to an enzyme, a chemical reaction starts, and this chemical reaction transforms these polyphenols into brown-colored pigments known as melanin. And that's exactly why the exposed surface of the apples turns brown, changes its color after a few minutes. And this causal explanation already reveals that our phenomenon is driven by a mechanism which in turn provides the underlying sequence of reaction steps. In this case, I already mentioned that polyphenols come into contact with the oxygen in the air, but I did not uncover the underlying reaction steps that transform these polyphenols into brown-colored melanins. And this is exactly where mechanistic reasoning comes into play. Mechanistic reasoning identifies, describes, or analyzes the underlying mechanism to infer, explain, control, or predict the target phenomenon. So mechanistic reasoning is in itself an epistemic practice for generating new knowledge and uncovering mechanisms. So far, I hope that I could demonstrate that mechanistic reasoning helps students approach these 3 questions of scientific inquiry and thereby helping them to engage with phenomena across the natural and engineered worlds. First of all, mechanistic reasoning addresses the ontic question of scientific inquiry as it allows students make observations, and it also provides a structured approach to investigating phenomena. Mechanistic reasoning can also explain why phenomena occur by identifying the underlying entities, activities, as well as their properties. And mechanistic reasoning is an epistemic question, an epistemic practice in itself that helps us to address these epistemic questions. Specifically, mechanistic reasoning shows how scientific knowledge can be constructed, for example, through the development of explanatory models. These explanatory models can be grounded in evidence, and this evidence can be derived from laboratory data or laboratory experimentation. However, the way the public engages with these three questions of scientific inquiry differs significantly from how science addresses them. Particularly, the natural and engineered world is partly misrepresented in today's fractured information landscape. On the one hand, the gatekeeping role of traditional media has eroded. Nowadays, everyone can share information, and particularly misinformation, at any time. Consequently, the amount of misinformation has significantly increased within the last few years, and individuals must now be understood as active participants of science communication who have to take over certain gatekeeping functions by themselves. On the other hand, due to the increasing specialization of knowledge in today's division of labor, we are becoming increasingly dependent on the expertise of others. In this context, philosopher John Hartwig coined the term epistemic dependence. On simpler terms, we have to trust that experts know what they do and tell us also what is true. In this context, science education has to equip students with the competencies to make informed credibility judgments. And here we distinguish between two different types of credibility judgments, so-called first-hand evaluations or plausibility strategies. Evaluate the plausibility of the content of mediated scientific information itself. By contrast, second-hand evaluations, or so-called trust strategies, help us evaluate the source, the authors of that information. And which of these two types of credibility judgments students can make depends heavily on their level of domain-specific expertise. Students with sufficient domain-specific expertise can directly evaluate the plausibility of a given claim by assessing the quality of the underlying evidence. By contrast, students with rather limited domain-specific expertise must rely on appropriate epistemic trust in the source, in the authors of that information, rather than judging the claim in itself. And we hypothesize that mechanistic reasoning may provide an entry point, especially for these first-hand evaluations, as it helps students approach phenomena across various domains. As we've heard already, mechanistic reasoning analyzes the entities and activities that produce regular changes from start to finish conditions. In this basic sense, mechanistic reasoning provides a dualistic analysis of phenomena by identifying entities and activities. And this dualistic analysis can be applied across phenomena, and even lay people may be able to identify the entities and activities within mediated scientific information. And second, mechanistic reasoning typically operates across a set of scalar levels. For example, mechanistic reasoning can include a subatomic, an atomic, molecular, macromolecular, or even a cellular, tissue, organ, and organism level. Mechanistic reasoning typically focuses on a narrow set of these scalar levels, and sensitivity to scalar levels and black boxes may help lay people judge whether information addresses the scalar levels that appropriately support that given claim. Our argument for the importance of mechanistic reasoning for approaching phenomena may align with a set of practices for credibility judgments commonly referred to as pre-bunking. Pre-bunking aims at neutralizing misinformation before individuals encounter it, because it has been shown that it is notoriously difficult to correct such information after it has been processed. Debunking builds on so-called inoculation theory. Inoculation theory suggests that people can be inoculated against misinformation by being exposed to a weakened or refuted version of that claim in advance. And just like a vaccine stimulates the immune system to resist future infections, inoculation messages equip individuals with counter-arguments that may help build lasting resistance against misinformation. And based on this conceptual foundation, we hypothesize that there can be a conceptual intersection between mechanistic reasoning and science literacy, especially in the context of these credibility judgments. On the one hand, broader discussions in scientific literacy, instruction, and research may enrich domain-specific mechanistic reasoning by focusing our attention to phenomena of broader societal relevance. And as I will demonstrate now, mechanistic reasoning may also serve as a diagnostic tool to assess the content-related aspects of students' credibility judgments, both in domain-specific and in domain general phenomena. And therefore, we want to investigate how students judge the credibility of information across a set of phenomena, here rather domain-specific and domain general phenomena. To do that, we designed two different tasks. The first task is our domain-specific task, and this is in our case an organic chemistry-specific task. This task prompts undergraduate organic chemistry students to judge the plausibility of alternative reaction products for different chemical reactions. Among other reactions, an intramolecular Williamson ether synthesis, which is shown on this slide. 4 fellow students chose one of alternative reaction products and commented on their decision. And students have to identify which of these students correctly predicted the final product of that reaction. They have to justify why they think this student correctly predicted that product. And finally, they also have to assess the other students' reasoning and point out any flaws or oversights. And we transferred this domain-specific task to a more domain general task. Here, a social media user, Thomas Lüdecke, claims that there's no correlation between atmospheric CO2 levels and ocean pH levels. 4 other users commented on that claim. And again, students have to identify which of these users correctly explain the relationship between atmospheric CO2 levels and ocean pH levels. They have to justify their choice, and they also have to critically assess the other users' reasoning. To analyze students' credibility judgments in this context, we refer to the essential epistemic heuristics for mechanistic reasoning by Stina Christ and her team. And these heuristics include considering the scalar level below the target phenomenon, identifying and unpacking all relevant factors, so entities, activities, and properties at that lower scalar level, and finally linking all those properties back to the target phenomenon at the original scalar level. And in what follows, I'm going to show how we use these 3 heuristics to analyze students' reasoning in response to our 2 tasks. So here is a student response to the first task, to our organic chemistry specific task. In this task, William claimed that 1,4-butanediol is the most plausible product of that reaction, and a student wrote, William's argument is wrong. This reaction is implausible since a hydroxide ion is a strong base. Due to the small atom size and low polarizability, the negative charge of the oxygen atom is localized, making an acid-base reaction more favorable than a nucleophilic substitution. And this student's response contains 3 elements which align with the 3 essential epistemic heuristics for mechanistic reasoning. First, the student considers the scalar level below the target phenomenon by identifying the strong basicity of the hydroxide ion. After that, the student unpacks all relevant factors. In this case, the student links the strong basicity of the hydroxide ion to its localized negative charge. And finally, the student links all those properties back to the target phenomenon at the original scalar level by claiming that an acid-base reaction, in contrast, would be more favorable than a nucleophilic substitution. To operationalize students' use of these three essential epistemic heuristics, we applied three related concepts. We operationalized students' use of the first heuristic through the concept of granularity. Granularity measures the scalar levels addressed in students' mechanistic reasoning. And here we distinguish between two different levels of granularity. A phenomenological level of granularity refers to reasoning at the level of the target phenomenon, as well as to reasoning that can be derived from chemical representations, chemical structures. In organic chemistry, it is, however, vital to also include the distribution and movement of electrons, and therefore we included the electronic level of granularity to address the scalar level below the target phenomenon in undergraduate organic chemistry. We operationalized students' use of the second heuristic through the concept of dystemy core ideas, and here we distinguish between two different sets of core ideas. Structural core ideas refer to properties that can be derived from structural representations, and by contrast, energetic core ideas refer mainly to thermodynamic or kinetic changes during chemical reactions. And finally, we also analyze the interconnectedness between different entities, activities, and properties in students' mechanistic reasoning. And here we apply the concept of causality to analyze the increasing level of causality in students' reasoning. And when we apply this operationalization to the example previously shown, this example is electronic as it already addresses the localized negative charge. It is structural as all properties can be derived from the chemical representation, so the structural formulas. And it is linear causal since the student links the strong basicity to the localized negative charge, which is in turn impacted by the small atom size and low polarizability. And we also applied these essential epistemic heuristics to the second task. Here is an example response. In this task, Thomas Lüdecke claimed that there's no correlation between atmospheric CO2 levels and ocean pH levels. A student responded that CO2 is a gas that dissolves in water, forming carbonic acid. This acid then dissociates into hydronium ions, which lead to a decrease in pH. Therefore, I do see a connection between the CO2 concentration in the air and the pH level of the ocean. Of course, the ocean contains buffering systems that mitigate the drop in pH. However, I believe these buffering systems only slow down the effect. So I do think the poster of Thomas Lüdecke is incorrect. We can analyze this response again through the lens of the essential epistemic heuristics. First, the student considers the scalar level below the target phenomenon by identifying the relevance of the hydronium ions in this context. After that, the student unpacks the relevant property, here the decrease in pH due to the dissociation of the acid. And finally, the student links all those properties back to the target phenomenon by claiming that there is a correlation between atmospheric CO2 levels and ocean pH levels. We again operationalize these heuristics through the concepts of granularity, dystemy core ideas, and causality. Our only difference is our operationalization of granularity. Here we introduce two different levels of granularity. A macroscopic level of granularity refers to reasoning that addresses the scalar level of the target phenomenon that refers to explicit observations. By contrast, the submicroscopic level of granularity refers to the atoms, ions, and molecules involved at the scalar level below that phenomenon. And applied through the example, this example is submicroscopic, as the student already identifies the hydronium ions that are relevant for that phenomenon. It is both structural and energetic. The decrease in pH is an impact of a structural property, here the dissociation of the acid. By contrast, the impact of the buffering system is a thermodynamic, so an energetic property, and we would analyze that as linear causal, as the student already identified the hydronium ions and the impact on the pH, which helped them to explain the connection between atmospheric CO2 levels and ocean pH levels. And I hope that I could demonstrate that there can be an intersection between mechanistic reasoning and science literacy in the context of these credibility judgments. Science literacy may enrich domain-specific mechanistic reasoning by focusing our attention to phenomena such as ocean acidification. By contrast, we could use the essential epistemic heuristics for mechanistic reasoning to analyze the content-related aspects of students' credibility judgments. And with that being said, I'd like to thank you very much for your attention, and I'm now looking forward to our discussion.
Thank you, Paul. Questions? I can ask the first question. If I don't see you, if you raise your hand, then later on just unmute yourself. Paul, I was wondering, I mean, this was very domain specific, the question that you presented. But eventually, if we think about misinformation, people will be exposed to, I mean, this was chemistry, but it's the same. I mean, these people could be exposed to something in biology, but if it will be the same, it will require the same domain-specific knowledge. Then how will this knowledge about mechanisms in chemistry will help them judge the credibility of something in biology, or that you're not suggesting that this is possible?
Yeah, so we address rather domain-specific phenomena in chemistry for two purposes. On the one hand, these phenomena are also relevant to misinformation, especially in climate change, where much can be explained by chemical mechanisms and chemical reactions. And for our students, this is our more natural entry point for fostering mechanistic reasoning. And I think what can be transferred to other domains is the sensitivity to scalar levels. So we try to emphasize that there are different scalar levels involved in any scientific information, and some of these scalar levels may be covered by black boxes, others may be uncovered, and to help students or even individuals to detect such black boxes can be first step. Of course, it is only a first step, because also other authors and pseudoscience can also include black boxes and unpacked black boxes in such information, but at least students get sensitivity that black boxes can exist, that they can look at the scalar level beyond the target phenomenon, and that there can be underlying mechanisms involved in phenomena that they may not be aware of. So this is our first claim for the relevance of mechanistic reasoning, of domain-specific mechanistic reasoning in this context. But of course, as the broader literature on credibility judgments also posits, there are many more strategies involved in that context. We are rather in the context of first-hand evaluations, which must be supported by the second-hand evaluations, so also providing strategies for evaluating the source of information, the role of peer review, the social processes of science, even the receiver of the information is possible. So this is a tiny piece where we want to start, but we also want to look at the bigger picture and want to go into this bigger direction step by step.
Okay. Thank you.
Thanks.
Tom?
Yeah, thank you, Paul, for the interesting talk. I think my question is related a little bit to what Michal asked and the answer you gave, but I'll ask her also. I'll ask it. So I'm missing a bit the connection of what you said with the misconception, the misinformation that is presented to students, and the connection to the theory that you used about the first-hand and second-hand evaluation. So it seems like what you presented here in the research is mostly about first-hand evaluation and information, where you have the students think about their understanding of the mechanism and the scientific explanation behind the phenomena. Where do you see the connection here to the second hand, or is it something that is for later studies to focus on?
To be honest, I don't even know if there could be a useful connection to such second-hand evaluations. As, for example, Jonathan Osborne proposes, there are other strategies involved like lateral reading or click restraint that more help address these second-hand evaluations. But from our perspective on mechanistic reasoning, I think we can learn from these discussions in science literacy and discussions on epistemic cognition to help students also be aware of that there's more than content involved, but also some epistemic practices like transitioning between scalar levels, identifying and unpacking black boxes. And this is kind of a way where mechanistic reasoning can contribute as a reasoning style. So also Jonathan Osborne and Alchin presented that vision for science literacy in the 21st century. And in one of their 4 dimensions, they postulated that reasoning styles are an important way of constructing knowledge and addressing misinformation. And I think that here mechanistic reasoning can also be a part of that bigger vision. Of course, there are many other practices involved, and the whole debate on credibility judgment is very complex, and mechanistic reasoning may contribute to a tiny bit of this vision. And we want to foster students in not only being aware of judging the plausibility of information about undergraduate organic chemistry mechanisms, but also to apply this knowledge in more broadly applicable phenomena or more broadly relevant contexts. Thanks.
Keenan?
Thanks for the great talk, Paul. I had a question about, you mentioned at some point how lay people think about different scalar levels, considering the presence of multiple scalar levels in an explanation. Could you just talk a little bit about if the literature says, or if you think, if an explanation has multiple scalar levels to it, if people find it more convincing or more credible? Is that what you've seen, or is that what the literature says? Or I was just kind of curious about just that domain general, like if people are talking about things underneath, that how that affects what they think about the explanation and its credibility.
I don't know in particular whether there are any relevant sources, but I know some articles that show that mechanistic reasoning in itself is very compelling for individuals and also for children. So they think that a mechanistic explanation, whether wrong or right, is more trustworthy than a non-mechanistic explanation. I think there are 2 or 3 papers out that address this claim, and I also think that Michal is a bit more into that topic and may jump in.
Other questions? Okay, so thank you again to all the speakers of this part. Now we're going to take a break We have 8 minutes break, and it's more than what we planned. So you can not only make yourself a cup of coffee, but also think about what you want to ask in our discussion, what philosophical questions you want to raise, or just more general questions about mechanistic reasoning and AI. So see you in 8 minutes.
We have 2 more talks for me for this afternoon, so I'm very much looking forward to that. And our first talk will be from Keenan Noyes. I'm not sure if you pronounce it correctly. And Jennifer Doherty, and they both come from the Michigan State University. And they are interested in mechanistic reasoning in the context of physiology or medicine, or both, or at an intersection of that. And so we will hear about how do doctors in training use AI and mechanistic reasoning for clinical diagnosis. So Keenan, you can start sharing and the floor is yours.
Awesome. Thanks for the introduction and to both Nicole and Michal for inviting us to talk about this work. We're super excited about some new preliminary data that we've collected regarding doctors in training use of AI and mechanistic reasoning in terms of clinical diagnosis. So to kind of give an overview of what I'll be talking about today, I'm going to first introduce existing models of clinical reasoning, how doctors arrive at a diagnosis. I'll talk a little bit then about some recent work that we've done exploring the role of mechanistic reasoning in that process, and then finally bring in that AI piece to see how AI is used in clinical reasoning and then how that potentially augments the role of mechanistic reasoning in this discipline. So to start, I wanted to talk a little bit about how a physician reasons clinically. So when I talk about clinical reasoning, I'm talking about this process by which a physician comes to a particular diagnosis. So a physician might see a patient who comes in, and maybe this patient has a fever, sore throat, swollen lymph nodes, little red dots at the back of the throat. And there's some process that a physician uses to get that patient's presenting symptoms to determine that, oh, it's probably strep throat. I should run a strep test and assuming it comes back positive, assign some antibiotics to this patient. Now, as I talk a little bit about the current models that folks use to conceptualize physician thinking, I want you to think to yourself how knowledge of that underlying physiology of all of those mechanisms by how the body works, how that is involved in this thinking process that a physician uses. So, like I previewed, modern efforts to think about physician thinking focus on dual process theory. And if this is a theory that you're not familiar with, it posits that there are these two frames. There's system 1 and system 2, where system 1 is this intuitive, automatic thinking. It's really fast. And system 2 is the slow thinking. It's very analytic and deliberate. And so this is the model that people use in the medical world to think about physician thinking. And so this here's a picture of this model. And it suggests that physicians rely on the system 1 thinking if they recognize the pattern, right? And by pattern here, I'm talking about the features of the current patient. And that can be everything from the context, the patient's risk factors, their symptoms. And so we have, if a patient comes in, or the physician will process what is going on in this context automatically. And if they recognize this pattern, they can use their system 1 thinking to come up with a possible diagnosis, run some tests, and then assign the official diagnosis as well as determine the treatment. In this body of literature, folks typically think about like what chess grandmasters do, how they have this robust repository of all the possible different patterns that one can do in a chess game so they can quickly identify what's the right approach that they should use. And in this approach, right, if you're thinking about, or if you're envisioning a physician using this system 1 knowledge, their understanding of those mechanisms is going to remain encapsulated. That's the word they use in the medical literature, but we might think about it more as they leave those mechanisms black boxed, right? And so those mechanisms by which this bacteria produces these symptoms, or those mechanisms by which the antibiotics treat this particular disease, aren't accessed in this frame of thinking. Now, physicians might shift into the system two thinking if they don't recognize the pattern, if they don't recognize what's going on with this patient. And it is in this system two thinking that folks believe that this is where a doctor would access this underlying biomedical knowledge. So if a physician would be reasoning mechanistically, then this would be happening during this system two period. But there's this broader question of, do physicians actually use mechanistic reasoning? And the literature out there is a bit mixed. So early studies of clinical reasoning, so pre-dual process theory, suggest that expert physicians don't really use knowledge of the underlying biomedical sciences. This could be because they were operating primarily in system one, unclear, but the studies out there say that they don't really use this knowledge. They don't really use these mechanisms. Furthermore, much of the current research that's focusing on improving physicians' clinical reasoning, improving diagnostic accuracy, it's really focused on that system one thinking, right? How do people use heuristics? How do we more accurately have our physicians recognize what's going on and immediately assign a diagnosis? And so in a recent position piece by Tonelli and Williamson, they highlight that the importance of mechanisms in determining causality is a current subject of debate, and the role of mechanistic reasoning in clinical practice has received far less attention. And so that was the impetus of our first study in this area, where we were looking at just initial perceptions of the role of mechanistic reasoning in medicine, since it turns out that it is such a kind of understudied area, or hot topic of debate. And so we interviewed 43 medical school instructors, asking them questions about what it means to reason like a physician and how mechanistic reasoning can help folks arrive at a diagnosis or treatment. And overwhelmingly, people did see that mechanistic reasoning was useful, which was great to see and encouraging, and meant that we could continue doing research in this area. When we probed a little more, right, to ask them a little bit about how mechanistic reasoning is useful, folks really saw it as contrasting pattern recognition or memorization. So here's a quote from a participant who says, "A tremendous amount of medicine is actually pattern recognition. It's not mechanistic reasoning, it's actually pattern recognition. The goal of a physician is to get to the diagnosis and the treatment, and they want to do that as fast as possible and as accurately as possible. So pattern recognition is the tool that they use." They also highlighted a little bit more about how and when folks will use their knowledge of the underlying mechanisms, when they'll shift into the system two thinking. So one common scenario that folks talked about was when a physician encounters an unusual and a difficult case where they can't rely on their system one thinking, they're going to turn to that system two thinking. And similarly, folks highlighted how doctors in training who don't have that robust pattern recognition knowledge to rely on, how they're going to primarily be forced to use that system two thinking. And this led to our follow-up study that has been done in collaboration with folks at the College of Osteopathic Medicine, like Dr. Carolina Rustini here at Michigan State. And in this research, we've been asking the question, how do doctors in training use mechanistic reasoning to generate differential diagnoses? And there's three parts of this study that I'll talk about, or like three key characteristics. The first is that this is a qualitative interview study, so I'll be talking a lot about quotes from talking to a couple participants. I'm asking for a differential diagnosis, which is something that I'll talk about very shortly. And also there's an AI piece in here, just how it aligns with this broader symposium that we're all here for today. So in these interviews, I was asking emergency medicine doctors in training, so people working in an emergency department, to think through a series of simulated cases. And so all of these simulated cases, they were based on real life scenarios. And for each of these cases, folks got a brief background history of the patient and some physical exam results. And then I asked them to generate a differential diagnosis. And what a differential diagnosis is a series of possible diagnoses that can act as a roadmap to guide what the physician does in terms of like ordering tests, trying to seek out certain lab values so that they can refine their diagnosis, rule things in and out until they reach the official and final diagnosis so they can proceed with a treatment plan. So in each of these, in these cases, I asked them for 3 possible diagnoses, and we're trying to evaluate if within those 3 they could arrive at the right diagnosis, and what was the reasoning they used to generate these diagnoses. Also, during these interviews, I gave them access to an AI called Open Evidence. So they're self-described as an AI co-pilot for doctors that helps them make high-stakes decisions at the point of care. And if you're unfamiliar with open evidence, as I was prior to starting the study, it's a big deal in the medical world. They have a really close partnership with folks in the US medical system. Specifically, this AI draws from research published in lots of medical journals. It's also free to access for US physicians if you've verified yourself. So like you actually have to like get your government doctor ID and use that, but then you get free access to this. And so I think going forward, this is going to continue to be a really big tool for the US medical system. Today I'm going to be sharing some preliminary results from this study. Because this is very new. I did these interviews like a month ago. So I'm excited to share it with you all today. And to kind of preview this, I want to first tell you a little bit about the participants that I'll be talking about. My goal is to talk to people or to talk to these doctors in training at each step of the emergency medicine pipeline. And I will also specify that I'm talking about the pipeline here in the United States. This might look differently in other parts of the world. So for these emergency medicine physicians, they start out with a 4-year pre-medical undergraduate program. They spend 2 years in medical school talking about the mechanisms underlying their clinical practice. And then they will move to their clerkship part of their training where they receive, in the hospital training. And then finally, at this point, they are now practicing doctors and they go on to their residency and fellowship. And so it's a rather long training process. And today I'll be talking with folks who are at the residency point of this process. Specifically, I talked to 7 emergency medicine residents. And while they're in, their earlier stages of the career, these are all practicing physicians. So the things that I'm asking them to do are reasonable, right? These are going to be cases that they're going to actually experience out in the real world. I will be talking about one particular case today, and it is a bit of a long one, but it is kind of important that you have the same background that the students had. And so I'll be reading it out loud to kind of work you through it. So the background of this case is that there is a 31-year-old female who is 2 weeks postpartum, and she presents to the emergency department due to diarrhea, vomiting, and decreased mental status, which means they're disoriented, decreased alertness, and altered thinking. This morning, the patient was found to be confused and difficult to rouse, so her husband called 911, the emergency phone line here in the States. Her husband states that for the past 2 days, she has had nausea, non-bloody vomiting, and watery non-bloody diarrhea associated with diffuse abdominal pain. Her last episode of vomiting was 3 hours prior to arriving at the emergency department, and he also states that she has been very anxious since delivering her baby 2 weeks ago. The patient has not had any sick contacts, recent travel, or antibiotic use. Her delivery occurred without complications, and this was her first child. She has allergies to penicillin, a history of anxiety for which she takes alprazolam, which is Xanax, and has a family history of hypertension. We also provide the physical exam results. So these are pretty common diagnostics that an emergency medicine physician will use. So her heart rate is 145 beats per minute. Her blood pressure is 150/80. Her respiratory rate is 32 breaths per minute. Her oxygen saturation is 89% on 5 liters of supplemental oxygen via nasal cannula. And her temperature is 104 degrees. She is responsive to sternal rub, but is disoriented, mumbling phrases such as, "I have to feed the cat," and "the plane is about to leave." Radial pulses are present and normal on both sides. Her heart sounds are normal, but diffuse crackles are heard throughout the lungs. Abdomen is soft, non-distended, non-tender. Skin is flushed and moist, and the remainder of the exam is normal. So this is a doozy of a case. And I can't pretend that I know all the stuff. So fortunately, I've partnered with people who do, right? A medical student named Connor McGraw has been very helpful to this study. And so in real life, this patient was experiencing a thyroid storm. And now, what is a thyroid storm, you might ask? Well, I asked open evidence because it's a very helpful tool here. And so a thyroid storm is basically a form of hyperthyroidism, where your thyroid, which is a little gland here that produces hormones that affect every part of your body, is in overdrive. And because of all of that hormone going on in your body, a bunch of your organs experience very strange behaviors and like high fever, tachycardia, high heart rate, high breathing rate, and it's generally pretty bad. Now, I asked all 7 participants to read through this case, think aloud through the reasoning, and to generate a differential diagnosis for this patient. And you can see here are all 7 of these folks and all of their different possible diagnoses and their differential. And you'll notice that only 2 of them highlighted that this could be a thyroid storm or anything wrong with the thyroid, actually. I'm going to highlight a little bit about the reasoning strategies that they used. I would say in general, it was not mechanistic. Folks are really focused on trying to fit particular symptoms with a diagnosis. So this is one particular participant who says, okay, you can get odd cardiomyopathies, which would explain her tachycardia and wet lung sounds, but I would expect her to be a little bit more hypotensive. Okay, the altered mental status and fever means meningitis is something I should consider, but the diarrhea and vomiting, they don't fit into that. Okay, eclampsia is also something to consider because of that blood pressure. So again, they're really just focused on what is the symptom and what is the diagnosis that would fit with that. And then what symptoms maybe don't fit with that diagnosis. Another tool that they used was risk stratification and considering probability and likelihood. So this person highlights a pretty common mantra that a lot of the participants talked about, that in medical school, when you hear hoof prints, think horses, not zebras. Common things are common. You see heart attacks every day, you see chest pain every day. So you really should be highly considering the really common things. Second, when it comes to emergency medicine, you always have to rule out the worst possible thing it could be. When somebody comes in with chest pain or shortness of breath, you got to think heart attack, right? So they really got to worry about the really dangerous and common things often. Now, where you see this in these interviews is that every single participant highlighted sepsis. And if sepsis isn't something you're familiar with, sepsis is broadly just an extreme infection that is leading to organ failure throughout the body. There are many possible things that can cause sepsis. So sepsis is really just a collection of symptoms, but it's a really big deal in the emergency department. Sepsis is, here in the United States, the 3rd leading cause of death of folks in the hospital. And it's typically diagnosed based on specific physical exam criteria. So for example, this person said, I think sepsis because she's meeting 2 of the 4 SIRS criteria. She has a really high temperature and a really fast heart rate. Another person says she could just be in full-blown organ failure, and that's where the cracklings in the lung are coming from. She has these all-over symptoms, which just could be because of sepsis. So I want to focus in on these 2 participants who did actually identify that the thyroid was the problem, and why they did so. The first one is terribly interesting in its based on their reasoning, because they were doing the same thing, focused on matching patterns of the symptoms and the diagnoses. Nothing was particularly interesting or didn't seem novel at first. They just kind of said, I think it could be a thyroid because of these couple symptoms I'm seeing. And later on, they explained that I was just kind of lucky enough to have a patient who was very similar to this one, right? It wasn't 2 weeks. It was like 10 days after she had her baby. But she was in a thyroid storm, and that particular experience enabled this physician to arrive at that diagnosis. Participant 209 was a bit more interesting because she didn't have that prior experience, but still arrived at the diagnosis of thyroid storm. So she starts off thinking like, oh my goodness, this is a tough one. What am I thinking about, right? She jumps around to a couple things and eventually says, okay, another thing that jumps out to me is a thyroid storm, like some association with abnormalities of the thyroid. She's tachycardic, she's hypertensive, she's got all these other symptoms that don't necessarily fit with the medication she's taking. And so she says, I'm going to use open evidence to learn more about this because I think this could be a promising avenue. And so she used the AI to gather more information about this particular possibility. So she typed in thyroid dysfunction postpartum. And she gets all this information. Okay, there's Graves' disease. It depends on the underlying etiology. It affects 5 to 10% of women in their first year after pregnancy. She gets some additional information that sort of aligns with this particular case, and then decides to look even further, focusing on the abdominal pain and the fever that this particular patient has. And that did eventually lead her to include thyroid or a thyroid dysfunction issue in her diagnosis. But I want to highlight two other students who also used the AI, but did not have the same success that this particular participant did. So one participant, as he was going through the diagnoses, he really latched on to the fact that this particular participant was talking about having a cat, even though it was more of a just kind of an incoherent rambling that the patient was experiencing. And so he used open evidence to get more information about women pregnant cleaning litter box disease. And that led to this possible diagnosis of toxoplasmosis. He tried to figure out more of the treatments, but ultimately this led to a diagnosis that was not reasonable for this particular case. Participant 211 asked open evidence to just full on make a differential. So this participant provided a whole bunch of key information regarding this person's, vital signs, some key bits of the background history, and asked it to just generate a differential. And interestingly, open evidence did not include thyroid storm here. It didn't include anything about the thyroid. It highlighted sepsis as being an issue, pulmonary embolism, again, common, really dangerous things that folks are going to see in the emergency room. But interestingly, there was another participant, and this was a pilot participant. So this was actually a fourth-year medical student who was in her clerkship rounds. And she did actually come to the right diagnosis here and used open evidence in a similar way, but not the same. So first off, she initially was like, okay, I think it could be something with the thyroid because it's pregnancy related because of these postpartum conditions and everything being out of whack. And so she kind of typed in this summary of what she saw, right? Unstable vitals, highlighting some of the key diagnoses here. And this time around, open evidence did include the thyroid in those first three possible diagnoses. And it actually totally aligned with the initial three that she was thinking of. So she used it to double check her thinking and came away just fine. 4 out of the other 7 participants didn't use AI for this case. And I'll just briefly highlight what they focused on instead. So some, their reasonings for why, I should say. So one of them talked about not having any experience, right? They're just not familiar enough with this particular technology right now. These are residents right now. So you'll have to imagine that when they began medical school 6 years ago, right, AI was in a very different place. Some of them instead, they didn't use it for generating a differential diagnosis, but instead focusing on medication. So like, is this medication something I can use for pregnant patients? Okay, I have a baby that weighs this much. How much Tylenol can I give them? Right? So kind of hyper-specific care questions rather than like help me generate ideas related to a possible diagnosis. And then another participant highlighted how they used this when they were stumped, right? They said, if I don't know where to start on a patient, like they said right now, they're treating a lot of kids on a pediatric rotation, then they're going to use this to maybe generate some initial ideas. But when it came to the cases that I showed this person, and I will say this person did not correctly identify the thyroid storm for this patient, when it comes to these cases that I showed them, they knew where to start, so they didn't have to use AI, right? So there's this barrier of like, you have to think about when you might need this. And I know I'm running low on time, but I promise I'm almost done here. My takeaways. So what are the takeaways? So in terms of AI use, this is something that might change over time, right? I was looking at folks over here in the residency part, but in the future, I'm going to be interviewing folks earlier and earlier and earlier in the process who will be younger when they are first experiencing having access to something like open evidence. Does that change then how they use this tool in practice? And then also, what about these doctors that are already practicing, that have been on the floor for 30 some odd years and now have this brand new tool, right? What kind of training do they need to use it effectively? And then also, how best should AI be used, right? So, some of the people used it to get new information to help them think. Some of them just straight up gave them the case and asked it to come up with a differential. But we saw that for two of these participants, the approach that they used or the information they decided to include in their prompting determined whether or not it even suggested the correct diagnosis here. And I also think there are some broader questions about thinking about how doctors in training think, right? Because all of these folks are really focused on matching diagnoses and symptoms. They really weren't thinking about mechanisms. And so this model that we have about, oh, if people slow down, they begin to think about the underlying biomedical knowledge, maybe that's not happening, right? Maybe we need a different model for folks that are learning how to be a doctor, right? Maybe this is just for experienced folks. And then also, how are these doctors in training actually being taught to think through System 2, right? These are folks that are being taught by experienced doctors who don't often use their System 2 thinking. How are they being taught to use their underlying biomedical knowledge of these mechanisms in practice? And then there's this other question of, does AI provide an opportunity to shift how we think about the role of mechanistic reasoning in medicine, right? Like all of this pattern recognition, all the system one thinking that we seemingly are training our doctors to be able to do, is that something that we can offload to AI? And then does that then provide us more opportunity to have physicians focus on these underlying mechanisms and how that can be used to hone in on a very particular patient and provide them the care that is right for just them, not an overall most likely case. All right. And I did finish under the half hour. So thank you all for listening, and I can take some questions.
Thank you very much, Keenan, for bringing us into the realm of medicine and diagnosing a patient. So the floor is open for questions if you have some. Michael, go ahead.
Thank you, Keenan, for this interesting talk. I wanted to ask, and I don't know if you have the answer for now, but maybe in your further design of your research. So, I mean, you said that there is only minority of them used the AI to, when you said it, like, help me generate ideas.
Mm-hmm.
And these were the parts when they actually tried to figure out what is the mechanism. I mean, they asked something about what they're actually doing is they're just giving the two ends, like how cats could be related to these symptoms, and they're trying to see what is the mechanism. And I wonder if you think that it's something that if you go to early stages, as you said, it's something that you can help them do this even more. I mean, because they are not expert in thinking about the mechanism, but they might be experts for asking the mechanism and seeing if the relations that they see actually fit.
Yeah, that's a really good question. I feel like that's something that we might be able to see more of or get more insight to as we focus on those earlier students in the medical school process. Like maybe because these students were already practicing doctors, maybe they were like, oh, I don't need to ask those types of questions anymore. But maybe like a second year student's like, I'm still really figuring this stuff out. I just want to ask the questions to learn more about these mechanisms so that I can try and put this together myself. I think that's a really good question. I'm very curious to see how the use of this tool might differ, especially as we ask those younger folks.
John? Okay.
Yeah, Keenan, great talk. Thanks. So I guess my question is about kind of practicality here. So if the vast majority of what physicians do is pattern recognition, does using mechanistic thinking earlier on actually help them become better pattern recognition experts, which it seems like what they have to do most of the time? Or does actually spending time thinking about mechanism and trying to figure that out actually detract from their ability to create these huge pattern sets that they're going to be using later on? And so is it really useful for us to think that our doctors should think mechanistically, or is that not actually kind of a false narrative?
It's a great question and one that we are thinking about lots. And I hope that maybe our later discussion of like philosophically, what's the role of mechanistic reasoning in these times? I think that could fit into there. one of the things that jumps out is that there's been some studies done in like the early 2000s that were beginning to look at the use of mechanisms by students. And what they found is that indeed using those mechanisms did help people to remember things better, remember diagnoses better. But again, what they were focused on there was using mechanisms, in their own words, as a mnemonic device, as a tool for remembering, and not as a mechanistic model, how many of us think about the use of mechanisms. And it's an open question. They really haven't, folks in medicine really haven't looked at how doctors in training use mechanistic models in practice.
Thank you.
Alan?
Yeah, I think my question goes in the same direction. I was wondering if, first of all, like is it not like reasonable that they do not use mechanistic reasoning? Because what they need to do is to know if it's reasonable that the symptoms are caused by this disease, and then make the decision. So for the decision-making process, maybe it's not necessary to do the mechanism. They learned the mechanism, so it's important that they learned it at some point, but they need judgment if this is the reasonable choice of the disease. So they're kind of, maybe you can assume that they're doing black boxing. They black box the mechanism, and they just go for causal inference, like, and that can explain why you don't see the mechanistic reasoning, because they need to make a decision in the end, and this process must be quick to some point if they're working in the emergency department. So yeah, I don't know. That was just I was wondering if it could be, or if you think that that this could be an explanation, maybe that they are black boxing the mechanism unintendedly, maybe.
Absolutely. I mean, I think that's a really interesting possibility. I think, because they are in such a fast-paced environment, like that one participant said, they have to use pattern recognition to do their care fast and accurately. The question I think becomes then, when does it break down, right? Like, so one of the other themes that came out of our initial study is like if a patient has multiple different diseases, right? Then maybe they need to begin thinking about the mechanisms. Or if they get a really unusual patient. So like when they were focused, when the first two studies that were I would say more standard patients. And this third one, being a woman who has just had a baby, all of the participants were like, okay, I already know this is going to be a tough case, because when postpartum women come to the emergency room, weird stuff happens, right? They present weird. And I think it's in those cases that potentially using mechanisms could be really helpful. For your kind of run-of-the-mill cases, absolutely. It seems like pattern recognition is the move. And so maybe what this raises is a need to help people figure out when they need to think about mechanisms, right? Maybe it's not for every case. That shouldn't be the goal, but when is it useful? And I think that that's just an exciting area to think about in terms of physician training and just medical practice in general.
Last question for this talk, Iris?
Yeah, I really like that talk, and I think that this issue of pattern recognition, I think even for experienced doctors, has been criticized, that it's really good a lot of the time, but some of the times it gets you in trouble. And I was kind of curious about the context, because I feel like this sort of intersects with the whole dilemma about teaching basic science in medical school. And, is it a waste of time? Isn't it a waste of time? And I was wondering, is it a very problem-based, or does it emphasize basic science? Because it seems to me that, that basic science component that tends to get belittled or criticized in medical education is critical for the mechanistic reasoning. And I think the mechanistic reasoning can help us get out of trouble a lot of times. And so I was wondering about like the context and how you see all these pieces fitting together.
Yeah, I think that's a really good question. So the two things that jump out to me from some of the prior studies that we've done with this is when we ask people about when we ask these medical school instructors, like, when are you actually getting to the mechanisms? They were like, it's when we're doing simulated cases with our students, right? When we're having them, kind of step out of that lecture setting and be like, okay, here's a hypothetical patient. What are you doing? What are you thinking about, right? Because those are the moments where they're like, I want them to think about the underlying science. So I do think like they see a place for it and a place for those basic science knowledge in medical practice. It's just really not clear what happens after, once they leave those classrooms, like how the participants then think about it being used. Because when I was asking these students about, where did you learn how to do this? Where did you learn how to diagnose? They'd say, oh, look, a little bit in the medical school. And then they would say, but really, I'm just learning on the job. Really, I'm just learning from the attending that I'm watching, right? Who is using a lot of pattern recognition, right? Because they are experts, right? They don't need to access those mechanisms anymore. And so very quick on, kind of the expectation becomes, all right, I don't need to use this anymore. And yeah, so I don't know if this answers your question, because I think it's a really big one and I don't think there's a clear answer. But it does seem like maybe there should be a little bit more mechanistic reasoning in what they're doing.
I see that.
Thank you. I'm looking forward to seeing the continuation.
Thanks.
Yeah, thank you very much, Keenan, for the discussion. And maybe we can continue after the last talk, because also your talk, Keenan, opened very interesting aspects around mechanistic reasoning. Is that actually necessary in some cases, and when is it necessary, and how can we make that important for those students, so that they can perceive it as something purposeful in their way of working in medicine. But we'll have our last talk now. It's Gur, and he's working with Iris Tabak at Ben-Gurion University. And the title is How Might Generative AI Shape the Public's Engagement with Mechanistic Reasoning? So we stay in the topic of today. So very much looking forward to your talk.
Yeah, I'm just going to need your help. Can you hear me? Because I had a power outage here, so hopefully everything is okay. Okay, good. So, like Nicole said, my name is Gur. I'm working with Iris Tabak, and what I'm going to present today is this talk about how might Gen AI shape the public's engagement with mechanistic reasoning. I do have to say, and I'll elaborate on that part of this talk, a large part of this talk, is a thought experiment. It's a bit theoretical, and we're going to try to use some data we have to think about the future of public engagement and the future of Gen AI. Okay, so we're going to talk about three intersecting circles here in this talk, and that is public engagement with science, and then public engagement with mechanisms, which I'm going to try to show, to exemplify by using two case studies. One is using data from our recent study, and one is actually a study published by a different researcher called Maurizio Mezza. And then once I try to show what does public engagement with science, what could it mean, public engagement with mechanisms, I'm going to drop in what we know today about Gen AI and then make this small thought experiment, trying to think what could be the complexities, how do these examples, how do these could these evolve when we start thinking about Gen AI? Okay, so the first thing that's really important for me to say that when I'm going to talk in this talk about public engagement, I'm not just talking about how lay people understand science. So up until now, we've been talking about students in school. We've been talking about medical doctors, and this is not just another layer of non-experts and how do they understand science, because public engagement is much more than just lay people understanding. And public engagement has often been described, first of all, as collaborative. And although I think we saw it in Michal and Moria's talk, working in the classroom can sometimes be collaborative. However, when we actually talk about significant engagement with science, it's almost always within a community, and it involves several people working towards a collaborative goal. So it's kind of like a very different kind of collaboration. It's always also very much distributed. And that means that in this collaboration, not all the people, or not all the persons in that community have the same type of knowledge, the same type of roles. They don't even have the same type of aims, and still they collaborate together. So, for example, it allows a person to be part of an environmentally aware community without actually understanding ecological mechanisms. And going back to Keenan's talk, and I think it really puts a big question mark of when would people actually engage with mechanisms in such a community. Another point, the third point, is that it's usually practical. I mean, public engagement is about solving daily problems, and that once again puts a very big question mark of when people would actually use mechanisms. And I'm okay. The power went out for a second. And the fourth point is that in this world of public engagement, people use multiple epistemologies. Up until now, we've been talking about the scientific epistemology, I think, in all of the talks, but we do have to understand that when we talk about the public, there are also cultural epistemologies, there's personal experience, so experiential epistemologies, and whether we like it or not, it's part of public engagement. And the last point is that public engagement with science is multi-directional. I think that's the one thing that really surprised me when I started studying about public engagement. And I think I'm going to try to explain what multidirectionality means further on in one of my examples. But just to be brief about it, it actually means that it's not just scientists providing information to the public, but it's also the public providing things to scientists. Now, these things can be goals, but it can also be, sometimes it can be data, which they provide with scientists. So I'm going to, like I said, present two case studies. The first is from data we collected from Reddit forums. It's an example of a community that's collaborating together to be engaged with mechanisms. And the second example, the second case study, is from a paper published on how, and I think in a very interesting way, mechanistic reasoning actually, and I'm actually talking about centralized mechanistic reasoning, and centralized knowledge of mechanisms disrupts public engagement. So first of all, we're going to present the first case study. And this case study uses or looks at a very special community, which has become known as the Bro Science community. Now, what is the Bro Science community? The Bro Science community is a community that addresses the practical aims of fitness. So it's a community that has YouTube channels, Facebook groups, Reddit forums, and they're all dedicated to fitness. So it's all fitness enthusiasts. Obviously, they have many practical aims. They talk about diets, such as intermittent fasting. They talk about fitness programs. They talk about performance-enhancing drugs. And it's really interesting to see how they try to fill in gaps they find in the science discourse, but also they try to use the scientific discourse to plan and make decisions. Like I said, they have various modes of communication. I don't have exact data, but we can imagine that it's predominantly male when we look at the YouTube channels. So it's mainly male broadcasters who give information. Obviously, it's not only male broadcasters, but that's the majority. And when we look at the distribution of knowledge in the background of people who publish things, we do find that it's very heterogeneous, although a lot of the people in this community who are considered knowledge brokers, meaning people who take information, actually look into, sometimes it's peer-reviewed papers, sometimes it's giving out their own experiential data, their own personal experiments which they did. So these are knowledge brokers. A lot of them actually come without any scientific or medical background. So looking at this, we can actually ask, do bros actually need mechanisms? Do they use mechanisms? And the short answer is yes. Mechanisms in this community are actually considered a badge of excellence. So there's a very interesting study, an ethnographic study by Underwood, and she shows how this community slowly started moving from just talking about what works and people just giving advice saying, I did this and that, and you should also do that, working from that into starting to explain why it works and actually using peer-reviewed articles and papers to explain mechanistically why the things they recommend actually work according to science. And this is actually a quote from the data we have from these Reddit forums of one commenter saying to another, well, you gave your personal experience, but you don't know how to science, because you need to think about mechanisms. You need to think about non-causes. Another reason why they look into mechanisms is, for example, when they try to extend or restrict generalizability. For example, talking about one diet, which is not researched, that's a gap in the scientific community, and then saying, well, it's really similar to another diet which has been researched. So we can imagine that the same mechanisms that work in one diet will actually work in another diet. Another way in which they use mechanisms is to validate causality. So this is like a complementary example of one Reddit user saying, I heard this program, this dietary program, is supposed to have metabolic benefits. It's supposed to have a mechanism behind it, but he really wants to know whether maybe it's just caloric restriction or whether this is actually mechanisms, metabolic biological mechanisms that lead to these benefits. But with all that said, we do have to remember that this is a community that works towards practicality. So we'll also find things like this. I'm not going to pretend I understand all the science because, quite frankly, I don't give a shit. So it's kind of like a very complex interaction between these forces, sometimes trying to obtain mechanistic reasoning, sometimes actually saying, there might be a mechanism behind it. That's great, but I really don't need it right now. So both science mechanistic reasoning, like we saw, it's collaborative. It's collaborative because it's not one person who is a knowledge broker and then just gives out his information and that's it. We looked at these Reddit forums and a message containing even a lot of information, peer-reviewed information, will get a huge discussion of people asking questions, making criticism, asking for elaboration, saying how this fits or doesn't fit with their own personal experience. So it's not one person using mechanistic reasoning, it's actually a community working with mechanistic reasoning. It's distributed because there's an assortment of roles. Some of the people here are knowledge brokers. They give knowledge. Some are critics. Some ask questions. It's practical because sufficiency eventually is determined by the individual. Each person there would say, okay, this is enough, or maybe I need to delve even further to find out more mechanisms about it. Sometimes it's curiosity. Sometimes, like we saw in the example before, it's not. And it's epistemologically rich because mechanisms are tested through personal experience. People will actually say, well, this fits or doesn't fit with what I know, and vice versa, meaning people will say, this is what I know, and then some people will tell them, well, but that's not how science works. So looking at that, this is now when I'm trying to do my thought experiment here, thinking, how might Gen AI change this discussion? How will it change both science or other online communities? So first of all, we have to acknowledge the fact that today, Gen AI is basically one person against the machine. So in a way, Gen AI cuts away all that rich interaction. It disrupts collaboration. It disrupts the distribution of engagement. And I think this is highly important. We saw it, I think, in the data even Michal showed. We see this in earlier studies, looking at how people make mechanistic inquiry. And mechanistic inquiry is almost always richer when there's collaboration behind it, when there's people who ask each other questions and sometimes criticize or maybe say some of the things here aren't that obvious as they seem to be. And Michal's example of how two students argue of whether there is or isn't a black box here is highly important because one person against AI does not do it. We also have to remember, and this study was mentioned before, study by Cruz and Lombroso, non-experts are highly susceptible to jargon-rich circular explanations. And that actually means, especially when we think about hallucinations made by AI, that non-experts on themselves will not always be able to recognize when AI has given them just a lot of jargon, but no real mechanistic information. And a new study I recently saw done in Purdue University shows that AI in itself has a lower ability than humans to recognize its own explanatory gaps. So we do need this constant interaction and this constant criticism from people, and I would say from a collaboration of people to work with the information Gen AI gives out currently. Another thing we have to remember is that Gen AI reduces the presence of the community, because if people can ask AI, obviously they will go a lot less into these Reddit forums, and we should ask whether this would actually affect this epistemic cultural identity and values. Would mechanisms stay a badge of excellence if it's just one person against the machine? And another last question here is, how will this affect data collection? Because people, they don't upload to the AI their new data, and then the AI distributes it to other users, what actually, and this actually happens in online community. And this is going to be even more important in the next case study I'm going to show. And this is a case study from a case that happened during the COVID pandemic. And it starts in February 2021, when there are social media claims of women experiencing heavy menstrual bleeding following COVID-19 vaccinations. So this actually starts on social media, and then it follows by an article, a paper actually in the Israeli press, which makes waves of women claiming there's this link between the vaccination they got and HMB. The official response of the medical community, of the scientific and medical community, is this isn't real. There's no data linking vaccines to HMB. And this is until February 2022, a year later. However, 7 months later, in October 2022, the scientific community actually acknowledges that there is a link between Moderna vaccinations and HMB. And the author of this paper actually asked, what happened here? Why is there a year of silence? And one of the, she outlines a lot of reasons, but one of the reasons is actually what I think should be called kind of like an epistemic top-down mechanistic reasoning. HMB is not researched in the scientific human community. There's really a lack of mechanistic knowledge about it. This causes systemic neglect to data because doctors would say, I can't think of any causality between vaccinations and HMB. They can't think of any mechanistic of any causation because there are no papers on HMB, so they don't collect data. They don't see correlations. They don't see patterns. They don't explore the causality, and this obviously perpetuates. It leads to lack of mechanistic knowledge. So a top-down epistemic approach contributes to a bias against evidence generated by the public. And I think this case is a very good example of why public engagement with mechanisms is multidirectional. It's just not just science educating the public, but sometimes also the public providing data to scientists. So once again, a thought experiment, how might Gen AI affect multidirectionality in public engagement? So Gen AI systems are once again, they're centralized, they're trained on historical data. And this inherently amplifies top-down epistemic structures. Once again, Gen AI itself has low ability to recognize explanatory gaps. And this case really highlights the question of whether one person, one woman in this case, accessing Gen AI, asking, could vaccine affect HMB? Gen AI obviously, most probably giving out the centralized answer of, we don't have any data about it. So it's probably, you need to check for other things. Maybe it's stress, maybe it's something else. And it actually lowers access to science by lowering multidirectionality, especially because if we don't have those social communities like Reddit, like Facebook, we don't have any way to look at people trying to say and to report that there is actually a phenomena here that is currently in a blind spot. And the last thing is that we really have to be careful with the fact that Gen AI will most probably say, according to science, this could associate science with Gen AI, even when it's making these mistakes, and ultimately erode trust in science. Maybe just some possible directions for solutions. So what we were thinking of is that, and that's something I've been working even before when we worked on black boxes. It's first of all to cultivate individual epistemic awareness towards mechanisms. And that is to make people recognize why a mechanistic explanation is needed and why it matters. But also to support them and understand the boundaries of mechanistic knowledge right after that. It's also to cultivate individual epistemic awareness towards Gen AI. It's to make people understand what the boundaries of Gen AI are and what's the relationship of Gen AI is with the scientific community. And maybe design learning environments that call for collaboration with Gen AI, but not as a replacement to the entire social network. And possible future in Gen AI, this is more like science fiction, maybe have AI agents which you can turn on and off and ask them, can you find gaps for me? Can you reveal more causal depth? Or maybe be more transparent about what is actually known here, what is assumed, what is inferred, what is unknown, and eventually maybe even explore collective uses of GenAI in which it's not one person against GenAI or with GenAI, but multiple people, multiple persons working with GenAI. So that's it. Thank you very much, and I'll be happy to hear your thoughts.
Thank you, Gore. You're right. You're right on time. So we have a couple of minutes to get questions to your talk if there are some, and then we can open the general discussion about today. Paul, go ahead.
Yeah, thank you very much for your talk. It was really, really interesting. And I wrote much down in my book. And you said at the beginning of your talk, the public engagement is collaborative and community-driven, it is distributed, and it is practical. Are there ways to put that kind of public engagement also into teaching, maybe high school teaching or undergraduate teaching, so to show that public science is not just an individual endeavor, it is not just something internalistic, but it is also collaborative and community driven, and it is functional and tries to solve daily problems.
Wow, thank you. That's a great and big question. I would first say that I think Iris would agree, this is partly our motivation for looking at public engagement. It's wondering how can we learn from it to improve science education or education. I really right now I can mainly highlight the problems. And the problems are that schools they don't only tend, we assess students on an individual basis in schools. For them to really recreate public engagement in schools, we'd have to assess a community. And we're not doing that right now in schools. Another thing, and I think Keenan like really emphasized it, is sometimes saying, okay, we've been teaching you mechanisms, but you were actually able to solve this problem without knowing these mechanisms. So we need to find a way to maybe, I don't know, make them reflect on how it did or didn't change the way they think about the problem. I do think mechanisms have a place in science education. Don't get me wrong. But it's a much more complicated place than how it's discussed in most school systems right now.
Yeah,
So
thank you very much.
I hope I answered your question.
It's a hard question. I think it's a question for all and for maybe in the next decades for us in research and teaching to transform that and not an effort of single studies or single research projects. Thank you very much. It was very interesting.
Karen. Or Karen. I don't know if you want to have it in German or in English.
Yeah, very interesting, Heiko. I just wanted to ask you one thing. There is this some studies showing that you mentioned that that sometimes in the community would quote like peer-reviewed articles and would even maybe use mechanistic reasoning. And I wonder if there's not the danger of motivated reasoning, that you only present those data that and information that kind of support your recommendation. So I would really like to know if you checked or if there's if the articles they post, if they contradict their recommendation or not. I think it's very important because it sounds super positive, but on the other hand, if they're only quoting what's supporting their view, then it's not very critical.
Yeah, well, obviously you're right. I would say that even scientists go in this path sometimes, so it's not just the non-experts or public. I can say that one thing is that we're right now less interested whether people are right or wrong in their logic. But from interviews I did make, it's quite interesting to find out that at least some people, when they choose who they want to listen to, the YouTubers, their go-to YouTubers, it's actually those who present complex explanations or complex arguments, in which they might say, well, there's evidence this way, there's evidence that way, but eventually, so obviously, there is this framework of epistemic beliefs of people who like complexity or dislike complexity. I'm sure that also affects it. But at least with the people I talked, so when people tend to cherry pick, and that's actually a word used in those forms, so they are familiar with talking about cherry picking, they usually get lower ratings. Okay.
Michal?
Nice. So thank you, Go. It was really interesting. And I want to ask you about the part of the collaboration, because I think it's very interesting. And I know that usually people use AI like just individually and ask the AI questions. But I wonder if we can think about the AI like an expert in a forum. I mean, maybe there are, I don't know if there are, but studies about forums in which there are experts, but there are also other people who are not experts that answer the same questions. And if we think about AI like an expert, and maybe it's not really hindering the collaboration, but it adds something to it. I don't know how it works, but I know that in these forums, sometimes people who are not experts also answer the questions. So it means that it's not just, it makes something like, on unidirectional, you only ask the expert and you just get the answer from the expert, but you also have this collaboration. Maybe some of the ideas from research about such forums can help us think about what would happen if AI would take the role of the expert.
Yeah, I think that could be true. I mean, do people let the expert intervene and then cut off the I have to say that in the forums I looked at, there wasn't this expert person. I mean, sometimes there was a knowledge broker, and people usually talked, or even YouTubers, which they quoted, which could be an example of that. I would say, however, that especially when we're talking about Gen AI or AI in general, it should involve people understanding what it means, understanding understanding its boundaries, understanding its failures. For example, the fact that it centralizes information, it doesn't do anything else. It amplifies bias. And we know that, by the way, not only from these, we know that from a lot of studies that talk about minorities working with AI or AI working on data of minorities. So that's a very interesting idea. I think in that people should be educated. Maybe this is the era where AI epistemics will go into science education or education, in which we learn what AI can't do and what are the pitfalls which are inherent to AI, because that's what AI does.
It seems as if we don't have any further question for Gur, so I would like to invite everyone to think about what we've heard today. Personally, I think we had a broad range of aspects related to mechanistic reasoning, different disciplines, and AI tools have been used as well, but not only. So we have a range of topics, and I would like to invite everyone to think about what is going on in your mind currently with regard to the talks of today, and also maybe what sparked your interest or a thought that you want to either share with us or that you want to continue thinking about. So I would like to invite everyone to think about that and then share that with the rest of us. So there's no right or wrong, but that's just collecting thoughts about what we've heard today.
I wonder about how we can tie the things we've heard today and think about, I mean, on the one hand, how, I mean, we know that AI is going to be central in the way people think, and it's very instant. People do it, it's very fast. It doesn't require hard work of searching. So it's just immediate information. And it might be one of the, I mean, it's like I said, an expert, but an expert that you can ask to replace your mind in the way you reason mechanistically. And it relates to Paul and also Gur's talk about how we can judge what we get from these from the answers of AI, not just in terms of credibility, but also in terms of the things we can do with this information and how we can just learn from it and see if it's relevant for us and how to better use it.
Karen, go ahead. I saw you muted
Yeah,
yourself.
I don't want to interrupt someone. Anyone wanted to say something? Was it okay? Okay, so I had two thoughts, and one is a bit related to what Michal said. It's super interesting, and actually to what Go also said, this process of how knowledge is like transported, you could say. Like I just noticed that like my kids have this whole world of knowledge about Minecraft that I have no idea where they know it from, for sure not from school, but they're bringing it, and it's like from all kind of sources, like from friends or from, and it's super interesting that some knowledge accumulation, you could say, that you can use for the game, for example, can come from other places than school. I mean, and these mechanisms are very interesting. This process of knowledge, how it goes from one place to the others, very, very interesting, I think. And if we have to think that school is like not the only provider for knowledge. I mean, that's maybe obvious, but how all these other processes, like, I mean, maybe with AI, we have to say that the knowledge source is like totally like a different place now in the ChatGPT, for example. So that's one thought. And the other thought is that I think sometimes we maybe overestimate this. If we say that mechanistic reasoning is in the system 2 mainly, maybe we are overestimating this whole thing, because I mean, we do know that we have system 1 that is very fast and very strong. And there's this article, I think by Zamo, who said like that system 1, the worldview, even though mechanistic reason had an impact on the judgment and on the argumentation and so on, still the worldview of people, which is like mainly said by system 1, is much stronger affecting the way people reason. So maybe it's not either or. Maybe we have also to consider how these two systems are somehow affecting our thinking. Yeah, that was just two thoughts I had.
I mean, probably what you said kind of goes back to it. I mean, Keenan, you used the system 1 and system 2 differentiation. And what went through my mind was that we were talking about, I would say, 3 different things today. On the one hand, reasoning about mechanisms. So kind of just perceiving them or identifying mechanisms and black boxes. And then on the other hand, we had reasoning mechanistically, kind of. So like learners expressing their thoughts on a mechanism, and then we had maybe reasoning in other ways, and Paul mentioned that epistemic games, maybe that people are like in Keenan studies, like the students are like playing because that's in the discipline, like how you make decisions and how you do that. So pattern recognition or getting the answer, getting to the answer, or making a decision could be an epistemic game as well. So these are like my thoughts, and kind of I'm a bit confused, like where is it a linear development? Is it something that, you know, is at the same level? Reasoning about mechanism, reasoning mechanistically, is one coming first to the other, or is that something that is at the same level? And sometimes maybe we just have to think maybe there are other ways of reasoning, heuristics. And so maybe learners are starting with that, and then we have to, you know, especially with the use of Gen AI, they are not thinking about deeper than they have to think about phenomena or mechanisms when they use that. And this makes mechanistic reasoning even more important. And I mean, we talking about mechanistic reasoning now since years and trying to get that across, that it's an important way of reasoning about phenomena. And it is even more important now when we have the tools that kind of can spit out what the mechanism is, so that I don't have to think about it by myself. And so it kind of reinforces the importance of mechanistic reasoning again, even after today, I would say. Also, given the shallowness of, is it reasoning about mechanism, reasoning mechanistically, or other epistemic games involved in reasoning.
I would also agree with that point. And I think one challenge is to make clear and explicit when to use mechanistic reasoning and when to use or engage in other epistemic games. I think Michal called that in her recent paper difference makers game. So identifying just causes and effects without the underlying mechanism and building on correlations, and also valuing this form of reasoning and clearly showing when is what epistemic game important. But I'm really engaged by Gu's talk, and I'm also thinking of how we can make mechanistic reasoning as an epistemic practice more collaborative, more community driven, and how we can show our students across education levels that they can elaborate together on mechanisms, and that most mechanisms are not straightforward and they cannot be written on a blackboard. They have to figure it out together, and to show that this knowledge is distributed. They need each other to construct such a mechanism and to understand that. And I think this is also a thought that popped up in my mind today, and that I have to think of. I think that's a really novel vision for mechanistic reasoning, and maybe kind of the ultimate goal that can align with the vision 3 of science literacy, and where we have to take much effort in the community to go that way.
I think building on that community aspect too, that it comes back to, you know, thinking about mechanistic reasoning and reasoning with mechanisms when it comes to communication. Like Michal was saying, like, you know, it's unavoidable. Like you will have to make decisions about what is black boxed and what is not. And AIs have to do that too when they're communicating with you, right? And I think that, you know, I think it's really interesting how when people like make decisions and justify and identify evidence, like, you know, maybe they're using mechanisms or maybe they're not. But it feels like with communication, there always has to be a decision about the way that mechanisms are talked about, whether people realize it or not. And I feel like, you know, going forward too, the communication piece is going to be even more important as we think about the role of mechanisms.
So I'm curious, Keenan, you said, you know, AI is black boxing what mechanisms and making decisions. And I guess based on how I think about at least generative AI, I'd say it's not making decisions. It's looking at the probability that other people have black boxed this thing rather than actually making a decision about it. which in a way gets to, again, when we think about like, I was really intrigued by, you have a group and you're using AI as one of the knowledgeable people in the group, sources in the group, and being able to decide, well, first of all, how do you prompt the AI to get the kind of things you want out of it, and how do you evaluate it, and how do you rank that? Once AI says it, is that the final thing and you may as well not discuss it anymore? Or do you actually pick apart what the AI said? So I think those are all really interesting things that kind of swirl around right now in my head.
Maybe also the thing that the AI actually builds on ideas of others makes it the product of collaborative work, right? Because eventually what you see is what other people already thought and talked about and how they reacted. So eventually it reflects something that was established by the community.
It's the wisdom of the crowd, maybe, the AI.
Stolen without attribution.
Yeah, thank you very much for sharing that. I've just looked at the time, and I think some of us could continue discussing that and going a bit more philosophical, especially Michal will probably go down that road. I was very interested today by the different talks, and I think this will stick in my head for longer, and maybe you feel the same. And I think this community that we kind of established over the years can grow, and it's definitely good that we have more disciplines here, that we also talk about medicine. So that was nice to have Keenan here today, and also Gus talk about like the society and the pro science communities, kind of to look into that as well. Kind of this broadens the range of science ed and mechanistic reasoning, or the topic of mechanistic reasoning in science ed. So that was personally, I think, a fantastic afternoon for me. And I would give over to Michal for some last words, and then we can close this.
Thanks. I think you summed it up very good, and I really enjoyed this virtual event. I thank NARST for giving us the opportunity to create this event, and I hope we will have future events together and maybe symposium in conferences. I think it's a very good community to think together about mechanistic reasoning, because now we know that collaboration is very important.
True words.
Thank you.
Thank
Good
you all.
evening, good night. Bye.
Thank you. Thank you very much. Thank you.
Thank you.
Okay, so good.
Very good.
So good.
Hi.
Hi. Was nice, right?
Yeah.
Nice. I liked
Is
it.
it still recording? I'm not sure.
Oh, I think
It is.
yes,
Yeah,
probably.
we should be careful what we're saying if it's still recording.
I don't think we have the ability to stop the recording.
No, we don't. But I think I liked it. I think it was very thought-provoking. Yeah, I'm not sure yet. I have to sit down and reflect on it.
I'm glad we did it. Yeah, I think it was good. And we're meeting next week, right?
Yeah. And
Okay.
then the difficult discussion can continue. Paul's very scared about the meeting next week.
No, I think it will be okay. I think we should think about it. I have to better understand the ideas here. This
Yeah,
I send the questions, but I think we will be able to make something good and interesting. And I think Gur's talk was also was related to this idea, right? So I think
especially that collaborative aspect of it that we haven't exploited in a good way yet in science education, I think. It's just always that very individual learning process of, that's and individuals should think about mechanisms, but not as a collaborative activity for all. I think Ira Kaspari is doing a little bit more in that direction, not just focusing that much on mechanistic reasoning, but on epistemic agency. And so that is the work that comes closer to that idea of how we can think about mechanism in a collaborative way. I'm not sure if that's already out what she published, but that's an organic chemistry. But she looked into the different roles that students adopt while figuring out a mechanism of a reaction.
Okay.
Yeah.
Okay, we'll talk about it and we see. I mean, some of the ideas I feel like I don't really grasp, but so it might be that maybe we need to focus on others, or once I will understand this better, I will be able to contribute something to these ideas. But
yeah, I think Paul is currently like kind of shrinking it down to its like chemistry. So mechanistic reasoning in organic chemistry also helps you to reflect on, as you said, the ocean acidification and the chemistry behind other phenomena besides organic. But yeah, so I don't want him to make it smaller than it could potentially be, but we have to figure it out.
Yeah.
Yeah, it was nice working with you again, Michael. Also, you had a lot of the organization on your side this time. So
no, it wasn't a lot, but it was okay. And I saw that our book is I mean, they have it on the website. I didn't know. It was a nice surprise.
Yeah.
And it's always good to work with you, Nicole.
Yeah, I always learn a lot from your work. It's always inspiring. So that's I like that. So now we finished for today.
Yeah, I have to go home.
Yeah. So we see each other next week then.
Yeah, great. See you. Bye.
See you. Bye.
Bye.